Hello, welcome to another day of physical science. Today we're going to finish chapter 2, which was all about motion. So far, I just remembered something I needed. So far, we've just been talking about one-dimensional motion, and I started talking about free fall, that if I drop this, it falls. And I actually introduced some equations for the distance something falls as a function of time if it started as rest, and the velocity something falls at is at as a function of time. And I'm going to jump straight into an example problem. Before I get started, sorry, quick aside. I want to remind this. Don't forget, those of you watching this live, today is the 10th. So if you're watching this on the 10th, go okay. But tonight is your first homework is due. Once again, as long as you're watching us on the 10th. If it's not the 10th, then your homework is already past due, I guess. Or you're time traveling. Your homeworks are always due at 11 p.m. Wednesdays. Chapter 1's homework is due the 10th. Chapter 2 homework is the 17th. Chapter 3 homework is the 24th, and so on. So don't forget, 11 p.m. tonight, your homework is due. Also, since you're not going to see me before then, your lab is due this Friday, the 12th, and that is due at noon. At that point, I'll open the next one. The lab that will everything due each week though is from the material the week before. So everything I'm covering this chapter will not be on the chapter 1 homework, will not be on lab 1. That will all be on the next set because I always have everything due a week after I cover it. Any questions on that?
Nope.
Cool. Let's get into it. So for my free fall question, I want to do an example problem. Let's say you've probably heard the thing before that if someone throws a penny off the Empire State Building, it would be going fast enough and hit the ground to crack the sidewalk. That is making one major assumption. But let's make that assumption and do a problem. And say someone tosses a penny off the roof of the Empire State Building, which is 381 meters above the ground, not including the antenna. This is like to the last place people can stand. If we ignore air resistance, and there's the big assumption there, and I'll come back to that assumption in a little bit. How long does it take for the penny to hit the sidewalk? And how fast is the penny going when it does hit the sidewalk? Now, what I say is the Empire State Building is 381 meters tall. That means if you drop the penny, the distance it falls is going to be 381 meters. And I said, part A, how much time does that take? And so what I'll do is I'll say, okay, if something is dropping, we can say the distance it falls is a function of time. The distance something falls is a function of time is given as d equals 1/2 gt squared. And so I'm going to have to take this equation, and using this equation, I need to solve for t. Now, it's not immediately rearranged to solve for t. I'm going to have to rearrange it. And so what I'm going to do is I'm going to multiply both sides by 2. By multiplying both sides by 2, I get 2d equals gt squared. I can then divide both sides by g and square root. And I'll find that the time it takes the penalty to fall, 381 meters, is just going to be twice that distance divided by g, the square root of. And I can say, if you drop a penny at the Empire State Building without air resistance, it would take it 8.81 seconds to hit the pavement. Any questions there on part A? Okay. Part B is how fast is the penny going when it lands? If you want to find how fast something's going, if it is dropped from rest, velocity in free fall, we'll just say velocity, the equation I gave before, is that velocity equals negative gt. So it's just going to be negative 9.81 meters per second squared times that time we just found, 8.81 seconds. This will often come up that to solve part B of a problem, you need part A. But either way, I can do that math and get this speed. This says that it would be traveling at 86.5 meters per second in the downward direction, which is really goddamn fast. Questions there? Sorry. I'm perpetually yawning. Okay, now this was assuming something just dropped. If instead of just dropping something, you start doing something more complicated, like throwing it up in the air, that is going to make these equations more complicated. And to be completely honest, more complicated than I'm going to get to in this class. But I will talk a little bit about if you throw something upwards. If you throw something upwards, and is this the version I want? No, I want this version. If you throw something upwards, what's going to happen? I'm just going to cover that figure for a second. Is that on its way up, it's going up. That means on the way up, it has a positive velocity. On the way down, it's going down. That means on the way down, it has a negative velocity. But at some point, I have to go from positive to negative. What that means is that right there, at its highest point, it is switching from having a positive velocity to a negative velocity. If you throw something straight up, let it get to the highest point and fall. At all points, the acceleration is negative g. When it leaves your hand, acceleration is negative g. When it hits your hand, acceleration is negative g. At the highest point, acceleration is negative g. At all points, the acceleration is negative g. That's going to be the same everywhere. But at the highest point, you're in between going up and going down, your highest point will always have a velocity of 0. And that at this highest point, it'll momentarily not be moving for a split second before it plummets back down to the earth. Now, kind of interesting thing about this, since the acceleration is negative g everywhere, there's a weird line here, it's because it should be in a different spot. You get to watch me fix things, sorry. I don't know how this got moved. At all points, since the acceleration is the same, it becomes a symmetric process. And that if I take this ball and say, okay, at this point right here, let's say I knew exactly what the velocity is at that point right there. If I know the velocity at exactly that point right there, that means I also know the velocity at exactly this point right here. And that at any given height, the velocity will be the same magnitude on the way up and way down. It will just, the signs will be different. That in the case of when this ball reaches the exact same height it was thrown from, the velocity of the ball will be exactly the same as the velocity it left this person's hand. It'll just be in the negative direction where initially it was at the positive direction. Okay. Now this is all assuming that in a vacuum, that air isn't slowing it down. But in the real world, air resistance will slow things down and affect it. And so we got to talk about what happens if there is air resistance. You see, if there is air, you will have friction between the falling object and the air. That's why when I throw this piece of paper, it goes off camera. That's why when I throw this piece of paper, it goes down slowly. It doesn't just plummet. And that's what air resistance is. That's how parachutes work. That's just in general how things affect. Oh, you know what? This would be good for air resistance. That if I take this balloon and this ball, well, you couldn't see the ball; it fell fast, but the balloon falls slowly. That is what air resistance is. Now, air resistance depends on a lot of factors. The size of an object, the shape of the object, the weight of the object, all of these will affect air resistance. And that depending on the size, shape, and weight, that'll be how much air resistance a thing feels. But air resistance also is affected by one other thing, and this is probably the craziest part of it. Air resistance is affected by velocity. That when you drop something, if you just drop it, the second you drop it, it'll feel no air resistance. But as it falls, it has an acceleration due to gravity. And as the acceleration due to gravity speeds it up, air resistance will increase. And what it is that as it goes faster, the effect of air resistance will get bigger and bigger and bigger. And what happens is that means the effect of air resistance will cause the acceleration due to gravity to get smaller. That the faster it goes, the slower acceleration will be. Once again, assuming that we have air resistance. And this will happen until you hit a maximum amount. You see, once something is, since the, once again, without air, everything falls at G. And when we solve problems in this class, I'm always going to ignore air resistance. So you can say everything falls at G. You can use D equals 1/2 GT squared, V equals negative GT. Those will work. But if you have air resistance, the acceleration of gravity will get slowed down. And the faster it's going, the smaller the acceleration will be, going from that negative 9.81 meters per second squared till it eventually hits 0. For all objects, there will be a point where air resistance will make it so that the acceleration is 0. This is called terminal velocity. And it will just be a point at which things are no longer accelerating down, but falling at a constant velocity. This would depend on the size of the object, the shape of the object, and so on, the mass of the object. But yeah, we can say that there'll be a set velocity that it can't go past. It's how parachutes work. Parachutes, when they open up, they change your terminal velocity, something that is small enough that you will survive landing on the ground. They don't necessarily slow you down, although they kind of do in nature when you first open them. But the reason why is what they're doing is they're making it so that your terminal velocity is lower, the max velocity you can have from falling. Questions though? Now, this was all assuming something going straight up, straight down, right? If something is moving at an angle, I got this monkey with a cape, weird things that I have. He has elastic arms. If I shoot him straight up and straight down, that'll follow all the equations we just talked about. But if you fire something at an angle, then instead of straight up or straight down, I shoot this way, so it goes off at an angle. That was barely wet. That's going to become a little more complicated. Because if something is fired at an angle, it'll still feel acceleration due to gravity downwards. But its motion in x, its motion horizontal will be a little different. Anytime you have something moving two-dimensionally, aka it's not moving in a straight line up or down, or a straight line left or right, but is moving in a path that is in both dimensions, you're going to have to deal with both dimensions separately. And we're not going to talk about all cases always, because that's complicated, but let's just talk about the special case of projectile motion. And projectile motion is anytime something is moving through the air, we're assuming no air resistance as of now, but has a horizontal component. And so it'll be anytime something is arcing through the air. If something is arcing through the air like that, what's going to happen is that it will still feel the acceleration due to gravity, but the acceleration due to gravity is straight down. That the acceleration due to gravity pulls it down. That me doing this and me doing that is the same for acceleration due to gravity. But the difference is there's now motion in the horizontal. And here's the neat thing, is that in projectile motion, there is no acceleration in x. That the velocity in x is a constant. And so all that will happen is it will get pulled downward as it steadily trudges on to the side. So one way you can see this, so I want to make sure I put these in order of when I want to do it. But I think I'm good to just show this. Is what I have here is a launcher that there's a ball cocked in here that's going to shoot straight up. And this little stick sticking up here is going to trigger it. And I'm going to set this blue car moving with a constant velocity. And what happens when this blue car moves with a constant velocity? The ball gets shot up and will land. And what you see here is that the ball stays directly above the cart and lands in the cart. See, the reason for this is that this is a nearly frictionless track. While the cart is moving across this track, it has no acceleration in x. And when the ball starts moving, you see the ball matches. That's because this ball also has no acceleration in x. That when in the air, doesn't affect it. It's just only y. And in fact, if I was to take the same card and not have it move sideways, but just have it just fire the ball straight up, straight down, you would see the exact same height and process. See, in projectile motion, once again, it's the projectile computer is doing two separate things. That if you're throwing a football at an arc, you can say that football is really doing two things at once. The football is just going straight up, straight down, and it's also moving sideways at once. The velocity in x will be constant. The velocity at y would just be the same as if it was just thrown straight upwards. Now, I said before, if you throw something straight up and straight down, the velocity at the highest point is 0. That is not the same in projectile, because the velocity because at all points there's a velocity horizontally. And so if you throw something sideways, the velocity at the highest point is just going to be whatever its horizontal velocity is. The y component, the component that's up or down, that will be 0. But only the y component will be 0. The x component will still exist. Any questions here? So here's another example that theoretically I have a demo and I tried to recode it, but all of my efforts to recode this failed miserably. So instead I'm just going to use this picture. This is a setup that has two balls. One that is going to drop. And did I actually? I forgot. I did find a video of it. And I didn't prepare the video because oops. This is the first time I'm going to use this video in class because I found it since last semester. And so what we have here, I'm going to pause before this goes, is two balls. One of which is on this little piece. This metal rod is going to move quickly to the right. When this metal rod moves to the right, the left ball is going to be dropped straight down. The metal rod is going to hit the right ball, and the right ball is going to be pushed to the right. Both of them have no initial velocity in y. One is just being dropped. One is just being shoved straight to the side. And what's going to happen is that even though one has a horizontal component, they hit the ground at the exact same time. They hit the ground at the exact same time because they both have the same acceleration in y. That the acceleration y is identical for both of these. They both will follow a distance d equals 1/2 gt squared. And so there are some height above the ground. They both hit the ground at the same time. Any questions there? Okay. This next bit is a classic physics problem. It's not the most humane physics problem, but it's, as I said, a classic. And the problem is as follows. A hunter wants to hunt a monkey. And they see a monkey up in a tree, and the monkey is hanging from a branch. And the hunter knows the second the gun is fired, the monkey will let go and start dropping. And so the question is, where should you aim? So here's the idea. They show a cannon here, and the cannon's aiming a little low, but the general idea is the second this cannon fires, so the second this cannon fires, this monkey is going to let go and start dropping. And so, yeah, where do you aim? Do you want to aim at the monkey, below the monkey, or I forgot what I said, but do you want to aim above the monkey, at the monkey, or below the monkey? I'm going to open up a poll and let you guys try to decide on this. Should have showed up, and we'll see what people say. Normally I open a poll like this, I give it a minute. So we got 16 to 20 responding. Give it 10 more seconds. See if the last 4 people want to respond. Okay. Once again, trying to kind of do this how I do in person. So here's the results. 2 of you said above the monkey. 3 of you said at the monkey, and 12 said below the monkey. So let's see if we can get people. So most of you said below the monkey. Is someone who said below the monkey? Do you want to explain why? Anyone? Want to unmute and say?
You gotta like read it. So like if
Okay.
you know where he's gonna be, you put your rifle there and then you shoot when you
Yep.
see him.
Okay. How about above the monkey? Anyone want to say why? Take that as a no. And we want to say why at it?
I said add it because I feel like the velocity of the cannon would be a lot faster than the monkey's gonna fall.
Oh, I'm ignoring that fact. I'm gonna say everything's affected.
All right.
It's gonna be a slow moving cannon.
Okay.
Okay. So normally I would show this in class and explicitly do it. Now with a gun with a different setup, but we're not in class. So instead I found a video of someone else doing it because honestly, this person made a better video than I did. So here we go. So like how I would do it, and this volume is probably a little high, so I'm gonna turn it down a little bit. What he has is a projectile launcher with a laser sight. As I said, I do have the same thing, but mine is not where I am, and I don't have this crane lift. And so we have the monkey with a target right on it. We're gonna lift this guy up. And he lifted it so that the laser sight is right on the monkey. And as I said, I don't have this nice of a setup. I have to do mine in like 124 in Evenden. And so right now that was aimed directly at the monkey. It wasn't below it. I should have paused a second later, but it was aimed right at it. You could see that from the sight. And so let's look what happens when it fires. Aiming directly at it, you hit it. You don't want to aim below. You want to aim right at it. And so this doesn't fully make sense right away. The idea of leading would seem logical, that you'd want to lead it because it's moving. But that only works horizontally. If your something's moving horizontally, you need to lead it. But up and down, you do not want to lead if it's going to drop at the exact same moment. And the reason why is that all things are affected by gravity the same. All things have pulled down at a rate of negative g. And so not only is the monkey going to fall with gravity, fall at g, so is the projectile. And the projectile, which you can kind of see in the side view, let me go back to the side view. Side view. Side view is that the projectile is going to make a parabolic path. It's going to arc. I mean, if I just show it to you flat, it's really obvious. If I show it flat, I can say that when this bullet is fired, the bullet will start falling down due to gravity. So will the monkey, or in this case, it looks like a ball, until they both hit at the same height. And so, yeah, the answer is you aim directly at it. You do not lead it because it'll be accelerating downward the same as whatever you're launching. Any questions there? I really miss doing this in person. It's kind of fun to do this whole thing across the front of the room. Okay, so other things with projectile motion. And I closed something by mistake. There we go. So anytime something's thrown upwards at some angle or projectile motion, the range is how we define how far it goes. Some without air resistance, the maximum range something will have will always be happen when you launch something at 45 degrees. A kind of interesting thing about this though, and hold on, I want to see. Nope, I don't have a video for that. Is that if the max is at 45, then less than 45 and greater than 45 have to overlap. And what actually happens is any two complementary angles will have the same range. What complementary angles means the angles add up to 90. So if you launch something at 30 degrees and then launch something out at 60 degrees, they will both hit the ground in the exact same spot. The reason why is one will take the more direct path, while the other one will arc up in the air and come back down. But any two angles that equal 90 will always have the same range, assuming no air resistance. See, if you do have air resistance is basically friction between the air and the thing. And though mathematically 60 and 30 should be the same, 30 degrees spends a lot less time in the air than 60 degrees does. 60 degrees spends a longer time in the air touching the air. And so if you have air resistance, that is no longer true. You'll have that the complementary angles don't add up. And you'll also find that the maximum angle is going to happen at about 38 degrees and not 45. Okay? Any questions on that? Side note, we're probably going to get out a bit early today. I still have one more con, but I'm just going to explain why. That shoot the monkey thing in person takes so much longer because normally between each shot I have to set it up again and I fire it like 4 or 5 times. So instead of adding material because we're online to make it more, I'm just like, that part's quicker. I'll let you guys out early. So we'll probably be out early today. Okay, that's projectile motion. I want to talk about one more type of acceleration. That's kind of the purpose of this chapter. Is talk about how acceleration affects things. And instead of just free fall, let's talk about what happens if something moves in a circular path. So I have this toy and I'm going to spin it. Let's say I spin it at a nice constant velocity. I'm not speeding up, I'm not slowing down, but going at a constant rate. One of the things we said before is that acceleration is anytime you have a change in velocity. Now, if I keep the magnitude of the velocity the same, spin it constantly, would there then be an acceleration? Anyone?
If you're remaining constant, there shouldn't be any acceleration, but that's like basically impossible.
Touche. It is basically impossible. I'm doing my best right now, but I probably am not perfectly constant. And if it's going at a constant velocity, you'd say, yeah, there's no acceleration. But I was very careful how I worded that. I said the magnitude of the velocity is constant. See, the velocity is changing, even if the magnitude is constant. If it's going at like 20 RPMs, RPM stands for revolutions per minute. If something is spinning at 20 RPMs and you look at a point on the side, even if it's not changing, even if it's staying at 20 RPMs, there's still a change in the velocity. Even though I just said, yeah, even if it's going at a constant rotation, there's still a change in velocity because velocity is a vector. And if I spin this, and here, I'll spin it so it's matching the direction on there. Oh, I don't know. Yeah, it's matching the direction. Right at this side, the velocity is upwards. And you know what? Let's let's use this. Over here, the velocity is upwards. At the top, the velocity is this way. Over there, the velocity is down. At the bottom, the velocity is that way. That as this spins, my chair is stuck, the velocity is changing direction. And so even if the magnitude of the velocity is constant, even if it was always going at 20 RPMs, even if the velocity at this point here is 5 meters per second, and the velocity here is 5 meters per second, and here is 5 meters per second, and so on, even if that is constant, the direction of the velocity changes. And if the direction of the velocity changes, that means the velocity changes. And that means there's an acceleration. Anytime something spins in a circle, there will be a type of acceleration called centripetal acceleration, where centripetal acceleration is the acceleration to make something move on a circular path. You see, there is something causing this acceleration. When I spin this, this string here, this rope, that is causing the acceleration. If that rope didn't exist, I just hit my table. If that rope didn't exist, it would move in a straight line. It wouldn't stay on the circular path. I didn't bring that upstairs. I have a thing I sometimes use for this, but it's in my basement. But yeah, if something's moving on a circular path, if you get rid of the circular path, if you get rid of the whole circular path, it leaves it. That's because there is an acceleration. In fact, if you take an accelerometer and put it on something moving in a circle, which I did here, and I'm going to, this thing's loud, so let's turn back off the music. When this thing starts going, and I'm going to kind of speed it up and then let it move at a constant velocity in a second, you can see this is showing an acceleration pointing inwards. It's showing an acceleration pointing inwards because even if it's moving at a constant rate, there's an acceleration to keep it on that path. And that's centripetal acceleration. Anytime something moves in a circle, it feels centripetal acceleration pulling it towards the middle. Now, the magnitude of that centripetal acceleration, well, centripetal acceleration is A sub c. Acceleration is A sub c is centripetal acceleration, is v squared over r. How strong the centripetal acceleration is the velocity of the object squared divided by the radius. So like, that would be like saying basically this spin versus like, I'm hitting everything, this spin, which I think is basically out of the camera, ow, that just bounced off that onto me. You know, big radius versus small radius. Whee. Anytime something is moving, there is a centripetal acceleration. The smaller the radius, the more acceleration you need. The faster you're going, the more acceleration you need. And what this would be is anytime something is turning or making a circular path, it must feel this acceleration. Well, this acceleration would just be how fast squared over the radius. Now, let's say you're driving a car and you bank a hard turn. You just make a hard left, right? And you try not to change your velocity. To have an acceleration, anytime you have an acceleration, something must be causing it. If you're driving a car and turn, what is causing that acceleration is friction between the tires and the road. I'm going to get into this a lot more detail next chapter when I introduce forces. But for now, just know that it is the friction between the tires and the road that allow you to turn. And by allowing you to turn, I mean give you an acceleration. But there's a maximum amount of acceleration your tires can give you. This is why you got to slow down to take a turn. If you take a turn real fast, you might skid out. That's because that the acceleration is velocity squared. Wow, that's really good typewriting. Over radius. That was impressively bad handwriting. That's because it's the acceleration is velocity squared over the radius. And so if you're going super fast, you might go more than the car can take. It's also why ice will. It's also why if you take the sharper the turn, the slower you have to go. That if you're just doing like a slow bank, you can do it real fast. If you're doing a 90-degree turn, you're gonna have to go slower. That's because the sharper the turn, the smaller the radius is. That's gonna decrease the velocity you can do it at. It's also why if the road is icy, you have to go slower, because that's gonna limit the max acceleration the car can give you. But anytime you move in a circle, you will feel the centripetal acceleration. Okay? Let's do an example on it. Oh, sorry, is that a question?
No.
Let's say you got a car going around a clover leaf, and they're traveling at 12 meters per second, which is about 27 miles per hour. I should change this problem to be an interesting one. And you're going on a turn that has a radius of 50 meters. What's the centripetal acceleration? If you want to find the centripetal acceleration, we're saying they're traveling at 12 meters per second or raised at 50 meters. The centripetal acceleration will just be v squared over O. And so I'll just say 12 squared over 50. Now 12 squared is 144. And so I can do this math. Okay. Does this make sense?
Yep.
All right. Let's do something crazy with this. To fully understand what I'm about to go through, I need to go a lot higher in the physics here, which I'm not going to do, but I just kind of want to show it because it's kind of a neat effect of this. Let's say I got a bucket of water, and I take the bucket of water and I spin it. What's going to happen is the faster I spin it, the larger A sub C is. And A of C might point down. But if A of C is pointing out because there's a force holding in place, and the larger A of C is, the more it's going to hold something in place. And if I go,
Question.
yes,
Kinda. Is this kind of like how if like a box truck or something has top, it's like top heavy, that kind of turn, it'll go with that and plop on its side.
that
Makes
is definitely related. That gets more into angular momentum.
I know it's
That
like
if it's
a
heavy, the
different
top will
situation,
pull
but
more, but it will be part of this too, because I haven't talked about forces yet. But I'll cover it next chapter. But F equals ma. So the more mass something has is also going to contribute here, and we're going to get into how mass is related next chapter. And so something like a heavy truck, if it's top heavy, there's more mass out there, and so it's going to feel this acceleration. This acceleration is going to happen, but the more mass it has, the more it's going to pull. And so, yeah, that is part of why. So what I have here, if I can get this to play, is I have a cup that I'm going to pour water in with some food coloring. And I'm going to place it on this platform. And what it is if I can spin this thing, I can have it upside down. As long as I spin it fast enough, all the water will stay in it. And all the water will stay in it because of the fact of the centripetal acceleration. That because it's accelerating out, it will stay in. And I can do it without spilling any. To show it another way, this is a pilot doing a barrel roll you can see in the background while pouring water. At all times, the water goes towards the cup. The water goes towards the cup because it's feeling the centripetal acceleration. That even when he's upside down, the centripetal acceleration is going to pull downwards. Okay? Any questions though? Or any other questions, I should say?
I just want to know, how many times did it take you to do that without making a mess?
Well, normally I do it right in the front of the classroom. So seldom I make a mess. The problem is stopping, because the process of stopping is the only time it normally makes a mess. And there has been multiple times that has ended badly. Quick fun story. The first time I did it in 124, which is where I normally teach physical science, when I used to do it, there used to be lights in the top. And the first time I tried to do it, I swung it up straight into the light, which instantly stopped it and had the whole thing pull on myself. But I've only done that once. I have, while stopping it, spilled some on the carpet before, but normally it's only I spill a tiny bit.
Okay.
You get good at it. I do it a lot. Okay. Okay, I'm gonna stop there. That will be the end of today. Once again, homework is due tonight. Tonight being the 10th. You have lab due the 12th, and I will start chapter 3, which is all about forces, on the 15th. I'll go post that next chapter as soon as I get off here. But other than that, have a good day.
Have a good one.
Have a good day.